Welcome to this video. My name is Phil and I'm a senior lecturer in astrophysics at the University of Lincoln in the United Kingdom. And in this video, I wanted to go over what a kilonova was and how that is different from a supernova, which most people are probably aware of what a supernova might be, but a kilonova is not the same. It's not produced in the same way. And that's what I want to go over in this video. So before we go into what a kilonova is, let's just recap supernovas. So the most common types of supernovas that you can get are type 1a, type 2. There are other types, so you can have like type 1b, type 1c, but they're a little bit more exotic and they have a few unusual things there. But the most common ones you'll probably come across are going to be your type 2 and your type 1a. Now the type 1a, these are thermonuclear. Now, what you have here is you have a white dwarf and a red giant in a binary system. Once that red giant swells up, some of that material is pulled off onto the white dwarf and then it goes supernova. And once that white dwarf gets to a certain mass, the gravitational energy there basically collapses it far enough that it actually heats up to the ignition temperature of carbon. And once it does that, then basically the entire white dwarf star goes into a supernova. There isn't normally anything left over behind when that happens. So this is a thermonuclear explosion from a type 1a. So at the center of that, the white dwarf star does not survive. So typically there's no remnant left over from that. However, the red giant star does survive and it can quite often lose its outer layers. So it gets the outer layers stripped off and then it will get a velocity kick into space. It kind of gets thrown out really, and there's no white dwarf left anymore. So that's what you're typically left with. The type 2, this is from a death of a massive star. So let's say you've got a huge star. It's a single star on its own. It has a core collapse. And what happens is that core collapses, it overshoots something like the neutron degeneracy pressure. You then get a rebound back out through the outer layers, which basically gives you your supernova. So that propagating wave from the core outwards is what then accelerates the outer layers out and you get this supernova. So that's a core collapse and that is a type 2 from your massive stars. And type 2 typically do leave behind a dense stellar remnant. So this is an example of essentially a neutron star. It's actually a pulsar, and that's fairly typical for a type 2. If you go bigger than that, so if the star is even bigger, that's when you start to get your stellar mass black holes. The supernovae that are then produced from these sorts of events are typically quite high energy, or they're very high energy. And if you were to look at a galaxy and a supernova went off in one of those, then what you would find is that it can actually outshine the whole galaxy. So here's an example of one. Here you've got a spiral galaxy, and kind of on the outer parts, which has been circled, you've got a supernova. And the actual luminosity of that, how bright it is, actually can exceed the galaxy itself. So these are very, very energetic events that occur with supernova. Now, kilonovas, these are not from the death of stars. What happens is you start with a neutron star. So you've actually already got a neutron star that has undergone a type 2 supernova already. So it's already had a supernova to become a neutron star. So all stars that become a neutron star are going to go through a typical sort of supernova event, most likely going to be a type 2. So that's what's happened here. You're starting with a neutron star. These are very compact stars that are about the size of a city, essentially. Very, very compact, very dense objects, but they're still very heavy. Now, to get one of these kilonovas, you actually need a pair of them. And you have a pair of neutron stars that are orbiting each other, and they are spiraling in together. So actually they're orbiting, but they're actually moving closer together each orbit. So they're inspiraling. It can also actually include a black hole. So it could be a neutron star and a black hole. It doesn't have to be two neutron stars. So it's just two of these dense objects that are inspiraling together. Now, when they get close enough to each other, they will collide. So they will inspiral to the point where they actually physically collide with one another. And that is the point at which you then get a kilonova. Now, the kilonova that's actually produced is between 1/10 to 100th the brightness of a supernova. And that's actually the remnants of the Crab Nebula you can see in the background. So these are not as bright as a supernova, hence why they're called kilonovas. They're not a supernova, so they are significantly less luminous than a supernova would be, but they are more luminous than a typical nova. And a nova is a much a less bright version of a supernova. Really, they can be recurrent, which means that they actually happen over again, and it could just be that it's a eruption from a star, so less significant than supernova, and then it can happen over and over again. So kilonovas are kind of in between the two, really, in brightness. And these kilonovas actually are a significant source of gamma ray bursts. So gamma ray bursts are kind of fairly short, very high energy emission from these stars, essentially, and they can be on quite short periods or quite long periods. You get short and long gamma ray bursts. But basically, gamma rays are in the highest energy part of the electromagnetic spectrum. So these are incredibly energetic events, and these are responsible for those sort of gamma ray bursts, or at least they can account for some of the gamma ray bursts that we actually measure. They're also a source of gravitational waves. So here you've got two neutron stars, and they are orbiting each other, and they are spiraling in. Now, as they get closer and closer, you can see you've got getting these waves produced. And as they get to the point where they're just about to collide, then the amplitude of those gravitational waves increases massively, and then we can actually detect that through the distortion of space as they pass through. So these events are significant sources of gravitational waves. And there's your kilonova there, which you could pick up optically as well as detecting the gravitational waves. So at the end of that, you do end up with a remnant neutron star, possibly a black hole. And the interesting thing here is if you've got two neutron stars that collide, you can get something like a massive or a supermassive neutron star, much larger than we'd expect, and it can have like a delayed collapse into a black hole. So you can get like these really big neutron stars that don't instantly collapse into a black hole, but have a bit of a delay and then collapse into a black hole, or you can get a black hole. So these do produce a remnant, basically, not like the type 1a, which doesn't produce anything. So there is something left over at the end of this. Now, this is the first kilonova captured by Hubble. And then again, this is in a galaxy, and zoomed in, you can see kind of over a few days how it's actually dimmed down in brightness. So Hubble captured it, and then the afterglow from that you can see actually reduces down. So this was in the optical, essentially, so you can visually see this kilonova. But at the same time, LIGO detected gravitational waves. So this is a gravitational wave detector. It's essentially a interferometer. So it has two directions, essentially. And the ones I've highlighted here, you can see that kind of line that's kind of upticking, essentially. What's happening here is that over time, so if you go on the x-axis, your time is increasing. The time 0 is at the point of the actual collision, so the minus time means it's going further back before they collide. That's all it really means. The y-axis is the frequency. So the frequency of that gravitational wave is increasing as it approaches the collision between the two neutron stars, or black holes could be. And also the color of it gives you the amplitude of the wave. So again, you can see the frequency increases and the amplitude increases just before they actually collide. Now, why is that occurring? Well, as they inspiral, the gravitational wave that is emitted is essentially the same as the orbital frequency of them as well. So the orbital period will decrease, which means the orbital frequency changes as well. That changes in line with the gravitational frequency or gravitational wave frequency. So that gets much higher, and you can see that plot there, the amplitude is increasing. Well, it's called strain here, but it's essentially relates to the amplitude of that wave. And it gets closer to each other, which means that the gravitational frequency is increasing, and then they collide. Then you can actually measure the kilonova. So thank you for watching, and if you enjoy, then do check out some of the other videos.